Hi there, this is Jacob Nash, and in this video we'll be talking about improper integrals. So, what are improper integrals? They are integrals that have bounds that are infinite. Well, that might not technically be the perfect terminology, but you'll see what I mean. There are two different types that we'll talk about in this video, and the first type is shown here. Whoa, the bound is infinity or negative infinity. That's how you know for this type that it's improper. So you might just be like, what do I do for that? Because luckily, solving the integral itself is the same process. But then when you're plugging in the bounds, what do you do? So we have to actually use limits. We have to say the infinity is stupid, so let's replace it with a different letter and do limit, and you'll see in a second how we do that. So here's an example. Let's say we have an integral from a to infinity f of x dx. Which one of these is stupid? The a or the infinity? The infinity, because a just represents any number, you know? So we're like, that's stupid. So replace that thing with a t. That's a little better, right? And do the limit as t approaches infinity. Limits help us here, even if you don't like them. Now, what if it's the other way around? Negative infinity to b, well, this time the infinity down here is what we want to replace with t. By the way, it doesn't have to be t. I just use that arbitrarily. Doesn't matter what letter you used. You could draw a spiral for all I care, but maybe your calculus teacher wouldn't like that. Whatever. Anyways, now, what if they're both like that? Ooh, then you can split these up. Remember our integral rules? And there's not a dx here. Apologies for that. I didn't make this um, picture thing. There's supposed to be a dx here. But anyways, you split it up at any arbitrary value, which we'll just say it's c, and we'll talk about that. C is any real number, but it's going to typically want to be something that's simple. Now, look over here. If the limit is finite, then we can say that the definite integral converges and the value uh, and the limit is the value of the improper integral. So if the answer we end up getting is a number, then it converges. So that means there is an actual area under the curve. Sometimes just because the limit goes to infinity doesn't mean that the area under the curve is not calculatable. It can be because you could get some kind of thing like this. So look, um, some kind of thing that's like this, and then like, oh, eventually it hits right here. So actually it is an area, but technically at infinity does it actually reach the x-axis. So it actually is a calculatable area. Whereas if it diverges, it's like too bad it never does get somewhere. So technically the area under the curve is not a finite number or the limit that we would end up getting. Um, and there's a sneaky way that you're able to figure out whether it will diverge or converge. If you get something like this, integral like this, where it's 1 over x to something, if it's just x by itself, it will diverge. If it's less than 1, it will also diverge. But if it's greater than 1, it will converge. So meaning if it's 1 or less than 1, then that means that it is not going to, and the limit that we would end up doing will not actually have a finite value. But if it's greater than 1, then it will have a finite value. Let's look at an example. Find the area under the curve for y equals ln of x divided by x squared for x um, greater than or equal to 1. So since it says area under the curve, we know that it would be an integral. And how do we choose the bounds? Since it says x greater than or equal to 1, we would know that it goes from 1 to infinity. And here we go. I just typed that out. That's not very easy to type. So that's why it has to look like that instead. So once again, we see this infinity and we say, okay, that's stupid. I don't want that in there. So we replace it with the t, but we have to have this limit right here. Limit equals t goes to infinity. This thing's basically saying, all right, it's okay to put a t here now instead of infinity. Now we do the integral of this, which It's right here. And obviously steps are skipped for the purpose of this video not being too long because it's not supposed to be about how to solve integrals. But you would end up doing integration by parts. Oh, sorry, my computer's about to die. Uh, ln of x divided by x squared. You can't do that. U sub won't work. Only integration by parts will work because if you do the derivative of one of these, then watch the video if you don't remember how to do that. So this is what you would end up getting, and then you do the same thing, one and t, then switch over to here. I got lazy, so I used the a different uh, description of how to do this. So you plug in t right here. So look at that, just like we would do. We plug in t and we subtract it by if we plugged in 1. ln of 0 divided by 0, that is going to be, uh, or sorry, 1, sorry. That would be 0 divided by 1, 0 minus 1. And then you can actually split apart these limits. And we can see that if we plug in infinity here, we get ln of infinity divided by infinity. Ln of infinity is just going to be 1 because if you look at the ln function, um, that's what it would be. And then divided by infinity, 1 divided by, or sorry about that. Actually, ln of infinity is obviously infinity. Sorry about that. Divide by infinity, so we would need to use L'Hopital's there. And then infinity divide or minus 1 over infinity. 1 or sorry, 1 minus 1 over infinity. 1 over infinity, 0. And by the way, that's not like 1 divided by infinity, you're always gonna get 0, and I'll explain in a second why, but you don't really need to know that right now. I'll say that in a second. So 1 divided by or we would actually end up just uh, you see down here, we would have just 1 over t after that, and we do L'Hopital's rule, derivative of the top minus bottom, or derivative of the top and the bottom. You do that, and you would end up getting, oh, like I said, 1 over infinity is going to be 0, so 1 plus 0, 1. Sorry that that went kind of fast, but it's supposed to be calc too quick. Um, all right, hang on a second. Okay, sorry about that. I actually, like I said, my computer's gonna die. So now let's talk about what I was saying before. How am I able to determine that this, I'm not even gonna say equals 0. I'm just gonna say whatever that symbol would be. You get 0. It's not really equals though. That's not really a proper thing to say. But how do we determine this? Well, actually, you just have to think about the function 1 over x, and it looks like this, does it not? And as if we plug in infinity as it approaches infinity, we do eventually get to 0. That's how you get that. That's the correct justification. You can't really just say 1 divided by infinity equals 0. So I just wanted to point that out. And you can do that same justification for other ones as well. All right, let's look at an example like this. How is this one different? This is the situation where both bounds are infinity. And for that, you have to first separate the integral, um, and we separate it by 0. So this is almost like two puzzle pieces that can connect by that 0. And why is 0 the value that's chosen? Um, it's really just because it's a simple value. You can actually choose any value that you want, but 0 is a good value to choose here. Now we do the same thing as before. We get rid of the infinities and plug different letters in, and we have T and R. Once again, doesn't matter which letters you choose. These are just randomly chosen. And you do the antiderivative of those. Don't forget your arctans. That's what these would both be. Luckily, it's going to be the same for both every time you do this. Now you do the same thing. You plug in. So we have tan, arctan T, tan R. Now, like why is it negative this time? Well, actually that's if you plug in these, it's going to be different because you do tan arctan 0 minus tan t. That's why you get minus tan t. Arctan t, sorry. Ugh. Now, what is arctan t equal negative? And it's going to be the same for both of these, what we end up getting. That's not always the case for right this part, but this time it is the same, and it's both pi over 2. Now, how do I know that? Well, that's one of those things where it's like um, you kind of have to just remember your unit circle, and uh, that the actual reason for this right here is you're actually thinking about it like this way. What value, if you did the tangent of it, would give you infinity and pi over 2 because there's a vertical asymptote there. So it's cut off right here, but that just is pi as the answer. So that's the way you have to think about it. You might just be like, I don't know what the heck arctangent of infinity is, but it's actually simple because you just have to think about it reversed. It's like what value of tangent would get me infinity? Pi over 2. And I don't know why it's not in this question, but I think that the criteria was that it had to be in between a certain value because technically there are other values that also give us infinity because tangent has infinite vertical asymptotes. All right, now this is a different type of improper integral that we're going to look at. Um, this time we might actually have both bounds as numbers and not like negative infinity, positive infinity, something like that. It might be like that this time. The only difference is that this time one of those bounds will be at a vertical asymptote or something of that sort, but almost always a vertical asymptote. So you'll see what I mean in a second. But in this case, let's say, what is this saying? All right, if f is continuous but not continuous at a, we're basically saying, oh, there's something stupid at a, like a vertical asymptote. If that happens, then once again, you always get rid of the thing that's stupid. The A is stupid since it's not continuous at it. And we say, all right, replace it with T. So it's the same thing as like before, but we just are replacing the A instead of an infinity because this time the A is the thing that's stupid. But over here, not continuous B, you would replace it with the B. But this is an important step. This time we always have to have a one-side limit. Now, why would it be A from the right? Because if it's the integral from A to the B, it comes from the right to get to A, and then vice versa for B. So that's a little bit reverse of what you would think. But if the interval is A to B, to get to A, you go from the right. To get to B, you go from the left. So that's why it's like that. Kind of weird, but all right. If f is continuous at, or sorry, on A to C. So it's basically saying C is the stupid thing. So something in the middle of A and B is stupid. If that happens, split it up and expose that stupid thing. See that C we didn't see here? Expose that thing. Separate it out and make that letter the like puzzle piece that connects them. C. Now the C is there and we can say goodbye to the C. Now we put limits for both of those and get rid of the C. The C is stupid because it's not continuous at C. And once again, I said, usually not continuous is due to a vertical asymptote. I don't want to say always, but almost always. So we're saying not continuous. We're almost basically saying if there's a vertical asymptote at that situation, which is why you don't want to throw away your knowledge of domain. So you got to know where you have to know where a vertical asymptote might be, just so you know. Now, direct comparison test. This is something where we're like, if we can do this, if we know this, then we know this about a different function. That's what this thing is saying. So we're saying I know this always looks like gibberish. They do that on purpose to try to confuse you, or maybe not. Maybe that's just me. Maybe it's not really that complicated. But to me, this looks like gibberish. Really, it's simple. It's like, let's say there's two functions f and g, and always g is greater than f, which means the line or curve that g is always above f. If that's the case, then we know that f will do the same thing as g. That's what this statement is saying. So if g converges, f converges. Um, and if g diverges, or if f diverges, diverges. Sorry. That's a little bit strange because you see it's almost backwards here, but it's like f converges if g converges. G diverges if f diverges. And that's only if g is always greater than f. Now, what if we have something like this where they switch? One is sometimes over the other and sometimes not. Unfortunately, that means you'll have to split the integral like we've done before. Split it at the value at which that changes. How would you know where that happens? You set the two functions equal to each other. Um, does e to the x squared converge? And technically, I skipped out some things of what you would say, but yeah. So does that converge? How do we know? Well, we don't really know just by that, but we can say, what function do we know? And an example would be e to the x. So since e to the negative x is uh it converges, we know that it does from 0 to infinity. Now how? Well, that goes back to earlier in the video. Converges means like if we do that integral, we will get a number, basically, is what that means. And that's exactly the case. And since it does, and e to the negative x is always above e to the x squared for all values, then e to the x squared also converges. That's the justification for that. And that's the end of this video. So apologize that I kind of ran through that quick, but just trying to speed this up. Thank you for watching.